When we were kids, we all dreamt of flying. Many of us still do, and the real lucky ones sometimes do it in their sleep. Sometimes we wish that the inexorable force of gravity would disappear for a while. But what if we said it doesn't really exist? You'd say, well, that's just wordplay. You can call gravity whatever you want. It doesn't change anything. Objects will still fall to the ground. That's right, but if you think carefully about some very familiar things, you may experience an overwhelming feeling when your picture of the world is suddenly changed by surprising and unexpected details. In today's video, why didn't Newton like his theory of universal gravitation? Why does gravity behave very strangely? How to communicate with parallel universes using gravity? What is gravity really like? And can it ever really disappear? Gravity. Every like is a drop of motivation. If our videos inspire you, share that energy with likes and subscriptions. Something is really wrong with gravity. Many people remember from school courses of physics that objects with different masses fall to the ground at the same speed, and even with the same acceleration, 9.8 meters per second. Astronaut David Scott even carried out a simple experiment on the moon. He threw a hammer and a feather next to each other. They did fall simultaneously. You too can easily check this if you take objects of different masses but with the same windage. Let's say a basketball and a bowling ball. By throwing them from the same height, you'll see that they will fall almost simultaneously, with a minimum deviation due to air resistance which can be neglected. This is extremely strange, especially considering the fact that everything else in the universe works differently. If we throw a rock harder, it flies faster and lands further away. 10 kilograms of TNT explodes much stronger than 1 kilogram. But here we see something strange. Bodies of drastically different masses fall at almost the same speed. It's as if the gravity of our planet has acted selectively in a different way for each object. If you keep thinking about it, you can get to the point that gravity acts selectively and differently on each atom in each piece of matter. Wow! Seems like it's really clever. Obviously, it can't work that way. But how then? That's what we'll be looking at next. And one more thing. Have you ever wondered about the weakness of our planet's gravity? Well, it's not weak, you might say. After all, the rockets have a really hard time overcoming it to carry even a small cargo into orbit. In fact, the weakness of gravity shows in ordinary things. By picking up a fallen key from the floor, you are overcoming the gravity of our entire planet. And there are no metaphors or exaggerations here. You're literally doing it. We're so used to it that we don't even realize how unusual and, well, suspicious it is. Keep that thought in mind. We'll come back to it later, and you may be shocked by the discovery. Right now, let's find out what's wrong with gravity that we might even conclude that it doesn't exist at all. It all started with Newton and his apple. Although in fact the story of the fruit that fell on the head of the great scientist is nothing more than a cute myth. According to Newton's biographer William Stukeley, the scientist watched the apple fall from a distance when he was in a kind of contemplative mood. He reflected on why the apple fell perpendicular or straight to the ground, rather than sideways or any other alternative way. Overall, the main worry of Newton wasn't at all the falling apple. He was more interested in the motion of celestial bodies. One of the main questions Newton was wondering about was, why does the apple fall to the Earth, but the moon doesn't? After long hours spent observing planets moving around the Earth, Newton suddenly comes to a seemingly paradoxical conclusion. The apple is dropped to the ground by the same force that rotates the moon around the Earth. Of course, we don't know whether this idea was the first in a series of subsequent discoveries, but the dome over the mysteries of the universe cracked once again. After coming up with his famous theory, Newton still didn't have any idea why gravitational force exists. He had some misunderstanding about it. Also, he thought gravity acts instantaneously. Despite the oddities, Newton's theory of universal gravitation became the foundation of physics for 400 years, until Einstein and his theory. To briefly illustrate the power of Einstein's impact on science and understanding of the world, two epitaphs are often cited which together add up as a poem. Nature and nature's laws lay hid in night. God said, "Let Newton be, and all was light." Epitaph by Alexander Pope, 1688 to 1744. It did not last, the devil howling. Ho, let Einstein be. Restored the status quo. Epigram by Sir John Collins Squire, 1884 to 1958. Newton showed some scientific courage by assuming the existence of some strange force that acts at great distances. At that time, people had barely come up with the ether, let alone any gravitational fields. Nevertheless, Einstein surpassed Newton in that sense. His assumptions sounded like a pure absurdity. With his general theory of relativity, Einstein assumed that gravity didn't exist, and the attraction is nothing more than a side effect of another, much more amazing phenomenon, the spacetime curvature. But to simplify and properly understand this insanely complicated stuff, we're going to go a little further. Let's conduct some thought experiment. What does a skydiver feel during freefall? Most probably, it's only the whistling of the air in his ears. He doesn't feel any gravity, although it hasn't gone anywhere since he jumped out of the aeroplane. Einstein thought about something like this. He was thinking about an imaginary man falling from the roof of a house. It was obvious to the scientists that with all other things being equal, any objects falling near this man would seem to him as if suspended in the air. Yeah, we don't take air resistance into account. It's like gravity has really disappeared. Well, it hasn't, you may say, because this man will instantly say goodbye to those illusions as soon as he touches the ground. And it will turn out that gravity has not disappeared. It hasn't, right? Well, it's more complex. Let's imagine another situation. You're in space, inside a spaceship. You and your rocket are actually traveling at a constant speed. In this case, you do not feel any weight. Objects remain stationary relative to you. If you touch any object, it will move in a straight line at a constant speed. In this case, you'll become an internal observer, just like in a textbook. You're not accelerating, you're not in a gravitational field, and all the laws of physics apply in your reference frame. Now, listen carefully. These two scenarios with the parachutist and the astronaut in a rocket are equivalent, according to Einstein. Nope, they're not alike, but they're in fact the same physical phenomenon. Alright, both such observers feel weightless, but is this enough to equate the state of weightlessness in space with the illusion of weightlessness at the very surface of the planet? After all, at the height of a parachute jump, we're definitely in the gravitational field of the Earth. And the rapidly approaching ground after the jump will quickly remind you who's in charge. But reality can sometimes be much more surprising than it seems. Let's go back to our example. A person in a rocket is flying at a constant speed. He doesn't feel this speed in any way, does not feel the motion at all if the speed and the landscape in the porthole don't change. And then suddenly our astronaut happens to see a planet in the distance, a little away from the main course of the rocket. An external observer might notice that the rocket's trajectory slightly turns on the side of the planet. And now let's imagine how an ordinary bubble level would behave at this moment on the ship. You may think it would show a deviation, as in the case of a turn. But no, even the most precise equipment won't show any deviation. You won't feel that you're turning, and no super-sensitive gyroscopes will show it either. Yes, inside the ship, a man doesn't notice anything. He's not feeling any force or experiencing any acceleration. As the rocket approaches the planet, it accelerates faster and faster. But the man in the rocket still feels weightless. Nothing's changed for him. It's as if gravity really doesn't exist. Let's recall Newton. His apple didn't fall to the ground because of gravity. Basically, the apple fell because it's heavier than air. It's as if there was no gravity, only a medium. Objects heavier than the medium just fall down, and objects lighter than the medium fly up. If you launch a helium balloon, it will go up, and if you fill the balloon with hydrogen, it will go up even faster. If you blow a feather off your hand, it will fly for a while, but if you throw a brick, it will fall straight down. It turns out that if gravity really existed, smoke would not rise up, and a fly that sat on a freight train would not be able to fly off of it. The mass of the freight train is so great that the gravity would have to hold the fly on that train, preventing it from taking off. Sometimes it's not right here. For the umpteenth time, we think this whole thing works weird, And it's about to get even weirder when we consider how much gravity has in common with a completely different phenomenon, acceleration. Okay, we're back to deep space again. What happens if you turn on the rocket engines and speed up to an acceleration of 9.8 meters per second squared? To the observer inside, all objects would remain stationary while the floor of the rocket would literally crash into them. Inside the rocket, everything will appear to be accelerating down toward the ground, and you will feel a force pressing down on your feet. The same force that presses down on you all the time you're on Earth. You'll feel exactly the same in the accelerating ship as you do at rest on the surface of the Earth. And let's be clear, we're not implying that staying at rest in a gravitational field is similar to accelerating in a rocket. We are saying that it is exactly the same thing. And we will, of course, again, remember Einstein, since he was the one who came up with the idea. However, we're still kind of confused. It can't be that gravitation and acceleration are the same thing. I mean, it's obvious that they're different. But what makes us think so? First of all, confidence in the nature of some phenomena of the universe. And this confidence is erroneous. In fact, it's just like that. Standing on the ground, you're actually accelerating, and there's no gravitational field. Yes, that sounds crazy, but if you dig through the insanely complicated math in the general theory of relativity, the bottom line is exactly that. Thankfully, the following information will make it all clear. So, how can we explain a rocket's curved trajectory without gravitational forces or gravitational fields? The answer is curved spacetime. The connection to acceleration is still not apparent, so let's look again from afar. This is what you can often see in visualizations of curved spacetime. It's not a bad visualization, but it's still a little misleading. This picture makes you think that there is some force at the center that inexorably attracts everything to itself. But in general relativity, there is no gravitational force. I mean, at all. There is no such thing. This is not a sabotage of scientists, not an oversight or an omission. This issue worried even Einstein and still worries the best minds of today. The repeatedly proved and reliably verified general theory of relativity has no place for such a concept as gravitation. It just doesn't fit into the theory. So, either the theory is wrong, or gravitation is not what it seems. But what is it? And here again we think of the example of the spaceship flying past the planet. Do you remember that our tools there didn't notice any turn, even though the ship's trajectory was curving? Well, the ship is actually traveling in a straight line, and space itself is curved around a massive object, together with the straight line. Yes, this is actually a straight line from the point of view of our ship. Now here's where it gets interesting. The massive object, which in this case is the planet, curves space, which in its turn changes the trajectory of the ship. Of course, there are no rails that guide the motion, but it looks just like this. That is, the matter tells the space how to curve, and the space tells the matter how to move. That's gravity. Well, it was there, and then suddenly it was gone. All that's left is acceleration and curvature of space. And if you think this is all just math, it's not. This is not just a picture of a solar eclipse. It's a picture that finally dispelled the last doubts of the skeptics of the general theory of relativity. And the scientific world has finally recognized the existence of the curvature of space. The picture was taken by the great English astrophysicist Arthur Eddington, and by calling him great, we're not exaggerating. Eddington is known as the man who discovered the nature of stars, along with Carl Schwarzschild and James Jeans. He was one of the creators of a new scientific field in the first quarter of the 20th century, theoretical astrophysics. But let's go back to our topic. At that time, Einstein's theory was still too implausible for many scientists. It needed a strong and clear confirmation. This could be an experimental test of the deflection of light beams passing close to the sun, exactly as Einstein had predicted. For example, a beam of light from a distant star passing close to the sun should be deflected by a small angle, and an observer on Earth will see this star in the sky not where it normally is. Under normal conditions, this effect is very difficult to observe because the bright sunlight makes it impossible to see the stars during the day. But such an opportunity occurs during solar eclipses, and Eddington took advantage of this opportunity. In 1918, Eddington and British astronomer Frank Dyson sent an expedition to the island of Principe, located almost at the equator near the Atlantic coast of Africa. This was necessary to better prepare for observing the total solar eclipse on May 29, 1919. The equator had the best conditions for such an observation. That eclipse was particularly convenient because the Sun was located against the background of the bright Hyades star cluster. Eddington managed to take 16 photos, mostly not too good because of the rain that fell every now and again. However, with the help of special calculations, it was possible to show that the deviation of the position of the stars is close enough to the one predicted by the general theory of relativity, and far from the one expected according to classical mechanics. Then the second expedition was organized to confirm the results. Eddington organized it in the town of Sobral in the Brazilian Amazon jungle. Einstein knew about the experiment, albeit in public he pretended not to be particularly concerned about its results. However, on September 5, 1919, he wrote to his mother a letter in which he mentioned that there was still no news about the eclipse. The long-awaited news didn't come on September 22nd when Einstein's colleague, another genius, physicist Lorentz, telegraphed Einstein the results of Eddington's experiment. A short time later, Einstein showed Lorentz's telegram to a graduate student, Elsa Schneider. She was delighted, but the scientist himself was completely calm. He shrugged off her reaction and the observations. Nothing that his theory is correct regardless of whether observations confirm it or not. So, how is it then? Gravity really doesn't exist and it's all just some cool illusion. What about gravitational waves? They've been discovered experimentally after all. So, what? Gravitational waves don't disprove GTR. Moreover, they were predicted within the framework of GTR. They are described by solutions to Einstein's field of equations. And basically, this phenomenon is nothing more than a usual simple effect, as ripples on sand or scattering circles on water. It's not some kind of force, it's just an effect, one that proves something but doesn't disprove anything. And now, when everything seems to be in place, let's make a small but important remark. All the things we've said about non-existent gravitation refer to the model of the universe described by Einstein in GTR. But GTR is just a theory, not the whole of physics. There are still gaps there that other theories are trying to cover, and let's not forget about the ultimate dream of all physicists, is the so-called theory of everything. On this path, modern physicists developed other consistent theories where gravitation exists and even as a quantum nature. The notorious gravitons, which scientists have despaired to discover, coexist with other physical phenomena. There are even opinions that gravity can flow from our universe to another. Nope, here we do not go far from the scientific discussion. Parallel universes and higher dimensions are concepts from physics and mathematics, not pure fantasy. Now, this is certainly hard to imagine. After all, gravity is not a river or substance. It's not something quite material. How can it go anywhere? It's like saying that the screen of your smartphone is flowing away and getting smaller. It's absurd, isn't it? Yes, but in the case of gravity, it's even stranger. In quantum theories, gravitation has an even more strange nature than in GTR, where it doesn't exist at all. Unlike everything else in our world, unlike matter and interaction forces, it's only gravity that can interact with higher dimensions. We cannot see, touch, hear hypothetical beings from the fourth or any other dimension, but we can notice their presence by distortions of the gravitational field. The gravitational anomalies foreshadow the discovery of the wormhole in Christopher Nolan's movie Interstellar. They were just the evidence that mysterious beings from the fifth dimension were very near, and they're doing something to our world. Now, interaction involves some kind of exchange. If we see certain manifestations of gravity from other worlds in our dimension, it means that there must be less gravity in those other worlds. It sounds strange, but it makes sense if we assume the quantum nature of gravity. Here's an example to understand this. Imagine seeing a light coming from another universe. You can automatically assume that this other universe has lesser light now. because the photons flew out from there and eventually reached us. If something increases in one place, then in another place it must decrease, right? So what if gravity, according to this logic, leaks out someday, completely, into some kind of other world? What would happen to our two worlds? And if we say that gravity is some kind of exchange, what do we change? What will come from out there instead of gravity?